Hi, and thanks for joining me in this video about non-convective low-level wind shear. In this video, we're going to talk about how winds affect aircraft very close to the ground in the lowest layers of the atmosphere. First, we are going to look at statistics. In other words, we're going to look at aircraft accidents over a number of years and see what kind of trends there are with low-level wind shear. The FAA did a study of aircraft accidents over the period 2003 through 2007, specifically looking at weather-related aircraft accidents. And they found that wind shear was a very small percentage of those accidents. As you can see in this graph, wind is the biggest cause of weather-related accidents, whereas wind shear is one of the smaller factors. Now, this is across all different types of aircraft operations. What we mean by that is Part 91, which is general aviation, Part 121, which is air carrier, and also Part 135, which is air taxi, air charter. The FAA analyzed the phase of flight for these weather-related accidents that were caused by wind shear, and they found that most accidents occurred during approach and landing, but also during takeoff and also maneuvering. So what this implies is that aircraft were close to the ground when these aircraft accidents occurred, resulting from wind shear. The FAA also broke down the accidents caused by wind shear according to the different types of operations. Part 91, which is general aviation aircraft, experienced during this period 35 accidents, and that was out of 37. So you can see that the majority of wind shear accidents were or occurred under Part 91 with general aviation aircraft. There were no wind shear accidents under Part 121, which is air carrier, in other words, the airlines, during this period of time. And 2 of the 37 wind shear accidents that happened during this period of time occurred during 135 operations. So once again, a very small percentage.
We're going to move on to definitions, and we'll take a look at how we define non-convective low-level wind shear. And there's a lot of definitions in here, so we'll go through each one of these. We'll start out with what is non-convective and how is it different than convective wind shear.
We'll first start out by defining wind shear. Wind shear is a change in wind direction and or wind speed over some distance.
And convective wind shear is wind shear that happens with convective clouds, typically thunderstorms, but also could happen just with cumulus clouds for that matter. So non-convective wind shear would be wind shear that happens not with convective clouds, no convective clouds around. So this winds by themselves, just causing strong shears in the atmosphere.
Wind shear can happen because of a change of wind direction. In the figure on the left, we see a surface map and a low pressure system with winds of various directions around the low. On the right, we see vertically through the atmosphere going up how the wind can change direction in a very short distance as you go up through the atmosphere. Wind shear can also be a result of wind speed changes. And in the diagram on the left, you can see a weather map of the jet stream and how the wind changes as you go across the jet stream. On the right, you can see vertically going up through the atmosphere how the wind speed increases with height, which is what you would normally expect. Wind shear can change in the vertical, meaning that wind direction changes with either speed and or height as you go up through the atmosphere. Wind shear can also happen horizontally on a weather map, and that could be either direction as you see on the left with a surface map, or in the figure on the right with the jet stream, you can see how the speed changes as you move horizontally on a weather map. Technically, wind shear is a vector difference between two different heights or two different locations, meaning that it's not just speed and not just direction. You actually have to account for both speed and direction, which means Mathematically, when we figure this out, we actually break it down into components. And we look at the component in the x direction, component in the y direction, and we figure out a shear vector. Sometimes that can be difficult. That is what the National Weather Service does. But when you fly, typically you're just looking at the winds at different altitudes or different locations and try and estimate how the wind changes over that given distance.
And then low-level wind shear, by definition, is wind shear that happens at 2,000 feet AGL or below. Typically, this happens when an airplane is coming into land on final approach or departing the airport. And low-level wind shear, whenever we talk about it, we're looking at big changes in the wind speed and wind direction over very short distances. And this is very hazardous to aircraft at low altitudes. Aircraft at low altitudes are typically smaller, not smaller, slower, and larger airplanes have a lot of momentum, so it's hard to change the momentum when they're on final approach or when they're taking off. And we'll get into those concerns and the physics behind wind shear in the second video. The way we quantify wind shear is the shear gradient. We look at how much the wind changes over a given distance. We did these calculations when we were looking at turbulence, shear turbulence, and there were some rules of thumb for calculating moderate and severe turbulence both horizontally and vertically.
The National Weather Service has some values of shear gradient that they use when classifying low-level wind shear. And specifically, one of them is that they will classify non-convective vertical shears when the wind changes by more than 10 knots per 100 feet in a layer that is at least 200 feet thick. And those values need to occur within 2,000 feet of the ground. And remember, these values of 10 knots per 100 feet need to be a vector difference. The Aviation Weather Center and also the Center Weather Service units will classify low-level wind shear when there is at least one or more pilot report of low-level wind shear within 2,000 feet AGL with a gain or a loss of at least 20 knots in indicated airspeed.
But we're going to use these shear gradients to talk about how it affects the performance of the aircraft. And it's really hard to calculate the shear gradient while you're flying. Usually this is done in pre-flight. But when you can see it in the response of your aircraft, then you know that you have strong shears. And the FAA defines severe wind shear as a change in indicated approach speed of more than 15 knots or a change in your vertical speed by more than 500 feet per minute. So, for example, let's say that you're on final approach and your airspeed is 100 knots. If the airplane is stabilized, power is set, the configuration of the airplane is also set, and the airspeed suddenly drops to 85 knots, you lost 15 knots, and that would be considered severe wind shear. Likewise, if you're coming down at 500 feet per minute and all of a sudden the aircraft starts descending at 1,000 feet per minute, that's a change of 500 feet per minute. And you can see in this pilot report from Traverse City, Michigan, they'll issue urgent pilot reports whenever the wind shear is severe, when it's more than 15 knots. Here, a CRJ departing Traverse City experienced severe low-level wind shear. The aircraft lost 15 knots while climbing out between 400 feet and 3,000 feet MSL.
The FAA uses the criteria of 10 knots or more in airspeed fluctuations to classify pilot reports of low-level wind shear as urgent. So urgent pilot reports are fluctuations of wind speed of 10 knots or more. At less than 10 knots, then those are routine pilot reports, and the FAA has the discretion to decide what the classification is, whether they are routine pilot reports or urgent pilot reports.
Another way we can classify wind shear is based on the wind shear profile, and that depends upon the flight path and also how the winds change with altitude. And we're looking here mostly at vertical shear, and we're looking at changes in wind speed, and not a lot in wind direction here, at least in these. But you can use wind direction. You can use the vector component, the headwind component, to calculate or figure out the shear. So we're going to look at aircraft approaching to land and also taking off, because the shear, the type of shear that you experience depends upon whether you're climbing out or descending. So we'll take this step by step. We're going to go through 4 different scenarios, and each one of these scenarios, we're going to look at it as if the aircraft is, we're going to look at each one as the aircraft departs the airport and as it arrives to the airport. So the first one is a decreasing headwind. So here's what a decreasing headwind looks like if you are on final approach. As you descend to approach the runway, notice how the headwind decreases as you get closer and closer to the ground. This is what you normally expect. You usually land into the wind, and because of surface friction, wind decreases as you approach the ground. So this would be considered a decreasing headwind. If you look at it, the shear profile for a decreasing headwind as you depart the airport, then as you climb out, the wind gets weaker and weaker with height. This doesn't happen very often, but still, nonetheless, it does happen occasionally. So in this case, this is a decreasing headwind on departure. You can also look at an increasing headwind, and also it depends upon whether you're approaching the airport or departing the airport. On approach, as you get closer to the ground, the wind increases as you get closer to the runway. And you don't see this very often, but it does happen. An increasing headwind on departure was what you normally expect. As you climb, the wind speed increases, and this is a result of the decreased friction at higher altitudes. Likewise, you can look at tailwinds, and you can look at them for approach and departure. You can look at increasing or decreasing tailwinds. Here we have a decreasing tailwind as you approach the runway. Getting closer to the runway, the wind decreases with altitude, or it decreases as you get closer to the ground. Normally what you expect as a result of increasing friction. We don't normally approach airports or land with a tailwind, but sometimes it does happen. And here's a decreasing tailwind as you depart the airport. Climbing higher, the wind decreases. Not something that you don't normally see, but it can happen with if you calculate the tailwind component as a result of the wind changing direction, believe it or not. An increasing tailwind as you approach the runway. On approach, the winds increase as you descend. And with an increasing tailwind on departure, as you climb higher, you get a stronger tailwind, and that's what you would normally expect if you depart with a tailwind.
Thanks for watching this video on non-convective low-level wind shear. There are other videos on wind shear on my YouTube channel.